Hello and welcome. Today I am Professor Dr. Mchem from Dr.Mchem Institute of Chemistry, University of St. Jamshoro. Previously I was discussing with you about XRD and unit cells and how XRD, this X-ray diffractometer, it works. What is X-ray diffraction, right? So these were the things which we were discussing shortly previously, and now today I have selected another very interesting topic which I've also I think mentioned in my previous lecture, that we'll be discussing the Bragg's law. So actually previously this process of diffraction, how it goes, first you should know about that. What happens when the X-rays hits the crystal, right? The crystal lattice. Now I have explained you what is crystal lattice. That is simply the separation between the layers, different layers of atoms that are arranged in an ordered system, and randomly there are many patterns they are forming in a crystal. But we just to measure or just to calculate the you can say that the distance between any two particular atoms, or the spacing between the any two atoms, we will select particular planes so that we will be able to look for the possible things which we are looking. So what happens when, what is our point is today, what happens when then X-ray hits a crystal, right? So what happens when it gets in touch with the first layer of atoms that are just when it shines on the first atom that is on the surface, you can say, and what happens when it goes a little bit more into the crystal, and what will happen when both the two parallel X-ray beams, they hit or shine on the crystal, how they are reflected or they are scattered off, right? And what happens when the first initial, I will tell you what happens, how the first ray, when it goes and it reflects out, and then, or it scatters out, and then the second one or some of the other rays, they also hits or shines on the crystal, and then they are scattered off again, right? But the second one that goes a little bit more inside the crystal lattice, or the second atom, or inside the layers of the crystal lattice, it covers an extra distance, right? And when it covers an extra distance, that extra distance is you can call it is the path difference, right? So it has something to do with the path difference, and that leads to 2D sine theta, that which is something to do with the Bragg's law, right? So this is today I'm going to explain everything to you in this lecture. So it's something very interesting, and it's very you can find this video everywhere, this topic everywhere on the YouTube, but I thought that I must share with my students in my way to follow the series which we are just following right now. And I think that I've been quite successful in discussing all the initial topics that are related to XRD analysis, because you need to know what is a unit cell, first of all, what are the different types of a unit cell, what this XRD has to do with a unit cell, right? And what it has to do with the crystal structures, and what are the crystal systems. I've discussed different crystal systems also with you people, that how many types of crystal systems are there, right? And I showed you the 3D structures which I draw by my own self, you can say. I drew them. So I thought that I must now go a little bit more further, and we'll see what happens when we are dealing with the Bragg's law. So I prepared a slide for you people so that I can show you how this whole process goes on according to this to Bragg, right? Who was a genius, who was a great scientist, right? So let's start and let's watch the video, the rest of the video on the slide. Thank you. Hello students. So just as I mentioned just right now that we are now going to study the Bragg's law. For that we need to understand the figures which are drawn here. You can see on the slide. Now you have to focus on the first figure, that is this one, right? So now here when you can simply here see these are this was simply a diagram that conveys us something about the X-rays that are initially, you can see they will shine on a crystal lattice, and then what happens, they are scattered off. This is what is simply being shown here, right? So when an X-ray hits a crystal lattice, what do we get? Yes, of course, the reflected X-ray. That is it. This is the incident and this is the reflected one, right? Now here you can see the two rays, that is A and B, right? So the X-rays strike the ordered atoms in, and this is what these red atoms are. These are all the ordered atoms in a crystal plane. These are different planes, right? 1, 2, 3, three different planes. And here you can see this is the first layer of first plane. This is the second plane of atoms. You can see here the atoms are all ordered, right? So now what happens here? The first X-ray hits the upper plane, right? This one, it hits the upper plane and is reflected or scattered, called, you can say, forming an angle called theta. You can see here theta, right? So it forms this angle between this incident ray and the first plane, right? So this is the angle theta. Here there are angles that are formed now, right? When that ray is scattered off. The second ray will also hit the second plane. Now this is the second plane, right? This is ray B. Now it will also hit the, you can say, this second atom, or you can say the second plane, right? Or you can say the second X-ray, right? This you can also call the second X-ray beam, and are parallel to one another. Now these are both are parallel to one. I wrote also parallel to one another. So after striking the crystal plane, they form an angle theta with respect to that of the particular plane. They form an angle theta with respect to this particular plane. Now the distance between any two atoms. Now here I have written here. You can see here that this one and this one. You can see these two atoms. Now the distance between any two atoms is equals to 10 raised to power minus 10, and we can denote this with a small d. Now here you can see this is the distance that is between the first atom and the second atom in the crystal lattice. This is a crystal lattice. So this is the distance between these two atoms, and it is denoted by d. Now here simply you can see it is 10 raised to what is this, how you will calculate it? It is exactly equals to 10 raised to power minus 10, right? And you also call it an interplanar distance. This is also called an interplanar distance. So so we can call it as the distance between the two atoms is on the order of an X-rays wavelength, which is also 10 raised to minus 10 meters. So this is something very important to note, that the distance between the two atoms is in the order of an X-rays wavelength, which is 10 raised to power minus 10, right? So now when these two rays, that is A and B, are scattered off, they will form a constructive interference. Now what type of interference is this? That is they are forming a constructive interference, as the distance they travel is the difference in that distance is a whole number, or you can say a whole number multiple of that wavelength. So now if we look at the wave A, this one, it traveled a shorter distance. From here it strike this atom and it is out, right? It's scattered out. Whereas this one, if we look at the second one, it goes and it hits the second atom, that is a little bit more down, and this is the second ray B, and you can see here it strike and it is also scattered out. The wave B traveled an extra distance, so they are in one phase as they traveled and some extra distance. So this distance from here to here is extra traveled by this ray B, right? So this to this and this to this is the path path difference. This is called the path difference, right? Which this ray B, X-ray B traveled extra. So we were just discussing about the Bragg's law. Now we'll come to the second figure, in which you can again see that this is again the continuation of the same figure, but I have explained few more things here. That is the first ray. There are two rays initially that are shined on the, or you can say that hit the crystal, right? So the first layer of atoms, this is the crystal lattice. Again, you can see different atoms ordered, or atoms arranged here. So now when there are two rays, rays A and ray B, right? When they hit the ray, the first ray, that is ray A, it strikes the crystal, the first crystal's lattice first atom, the first plane's first atom. This atom, it would just scattered off, right, and forming an angle theta between the first plane and the incident ray, right? Whereas the second one, that is this one, the B, it traveled a more distance, an extra distance, which we call it a path difference. And this is like here, you can say this much is the extra distance traveled by ray B, which is not traveled by ray A, right? So it traveled a more distance, so it has covered an extra distance. So, and this is, you can say this, and the distance between the two atoms is, you can call it D, that is atom to atom is D. So separation between the two atoms is 2D sine theta, or you can say D times sine theta, or 2D sine theta, we will call it. So this is the path difference, right? This is the path difference, this is the path difference, right? So the two path difference, that means this path difference, that means 2D sine theta. One path difference, that means 2D sine theta. The two of the path difference equals to 2D sine theta. So this is the relationship, and 2D sine theta equals to n lambda. And what is n? N is the, you can say, a positive integer, having values 1, 2, 3, 4 and so on, or number of, right? So it is a positive integer. N could be any positive integer, 1, 2, 3, having the numbers 1, 2, 3, 4 and so on. So, and lambda is the wavelength of an X-ray, right? So now we have the relationship that is called Bragg's equation. 2D sine theta equals to n lambda, right? This is the Bragg's equation. Now here again I've mentioned also that this is the separation between the two atoms, or you can call it D times sine theta, or when you will calculate both the distance, that is the path difference this side and this time the two path difference, they will equal to 2D sine theta. As you can say here, you can see the two triangles, right? And you can see the angle between them, the theta is there, right? And the one theta, and this is another theta, right? So this is the perpendicular form. So you know that sine theta comes from sine theta equals to perpendicular upon hypotenuse. So this is the you can say simply it's perpendicular. So this sine theta comes from here. So then you will simply call it 2D sine theta, or you can call it the path difference equals to 2D sine theta. That is the two path difference, they equals to 2D sine theta. So this was the second plane. Now this relationship would be called Bragg's equation. That is n lambda equals to 2D sine theta, where m could be, or where n could be a positive integer. It can be 1, 2, 3 or 4, and d is the separation between any, you can say, two atoms. That is, you can also call it is a size of the slit or size of the opening, right? And lambda is the wavelength of the X-ray. What is lambda? Lambda is the wavelength of the X-ray. And theta is the angle of the, you can say, formed between the plane of the crystal lattice, that is this one, crystal lattice, and an X-ray, incident X-ray, that is this one, the incident X-ray, and the crystal lattice. So this equation basically gives us the idea that where these two waves will interfere constructively. It orients us also that it's where is its location. It gives us the idea about its location. And it was, as I told you before, derived by an English physicist who played a great role in driving Bragg's equation. So this equation is very helpful throughout. And if you know for example, the value of d, and if you know the value of theta is calculated, then that is the separation d, distance d between any two atoms can easily be calculated. The distance d can easily be calculated. So this is the Bragg's equation. So students, I was explaining you the Bragg's equation, and I showed you how these rays, when they are shined on the crystal lattice, how they got reflected or scattered off, and how the second ray, what is the behavior of the first ray that goes above that lattice, that is the first few atoms, and would be the behavior of the second ray that goes a little bit more deeper and hits the second atom, and then it covers an extra distance. So now one thing is very interesting. This equation, that is n lambda equals to 2d sine theta, which we call it a Bragg's equation, is very helpful if you know the lambda, if you know the value of lambda, that is wavelength, and if you know the theta, if you have calculated the theta is calculated, then the separation distance, that is d, between any two atoms can easily be calculated, right? So this Bragg's equation is the basis of the process called XRD, or X-ray diffraction. So now here we have gone through all the things that were necessary to cover this topic. So now we have come to know that the beam of X-rays shines on the crystal that contains a number of atoms in a plane, and that atoms gets hit and is scattered off. That ray is scattered off, and then some of the X-rays will go further down to the second series of atoms and travel an extra distance d called 2d sine theta, that is path distance, and the path distance equals to 2d sine theta, and then it is also scattered off. The two beams were in the phase, in one phase, in phase you can say, when they hit the atoms of the second beam, traveled that is extra distance than the first one. So this is simply the extra distance called the path difference traveled by the second beam. I hope you find this video very interesting, and I hope you will be able to understand now what is Bragg's equation, and what happens when these parallel rays, they hit the crystal lattice, right, the first plane and the second plane, and how the second ray, it covers the extra distance, and then how the separation between the two atoms equals to d times sine theta, or 2d sine theta, and which is also called or you can call it, that is the path difference is calculated, and it equals to 2d sine theta, that is the two path difference equals to 2d sine theta. So I hope that you will find this video interesting to share, interesting to learn, and interesting to follow Bragg's law, right? So I took the references in making this video from X-ray diffraction and Bragg's equation from AK lectures. You can easily find these on YouTube, and I took another reference, that is I could refer to this video to another. I took the reference from the chemistry, liquids and solids by Michael van Biesen, and another, well, you can say video I refer to, that is 26 X-ray diffraction, UTEXA, Senquest. So these were the websites from which I took the references, and I took the examples, and I need to follow this whole Bragg's law from these videos from these particular websites. So please go through them. Also the original videos, you can go through the original videos, and you can follow from those great physicists who were explaining this Bragg's law in their own way, because as I told you before, that when a physicist explains something, that is totally different rather than a chemist. So I hope you enjoyed all this thing. I would like to see all these things again in a close, you can see in a close view. I can show it to you so that you can see how this whole thing processed, right? And here, this is the second figure, this is the second, again the crystal lattice, and you can also see here again, right? So this was something very interesting, and this is the most important thing, that I have drawn all these things with my own handwriting for you people to follow and to understand Bragg's law. Thank you so much. Hope to see you again in the next video. Hello students, I'm back again. This is Professor Dr. Moina again, back to you. So I've been through all that very tough, long, topic, and I thought that I must end up this XRD today with this Bragg's equation and this Bragg's law, and I hope you find it very interesting and you will be able to solve different problems by applying this Bragg's formula. You will be able to calculate, as I've just told you, that if you know the two quantities, you can calculate easily the third one, right? So if I will get some time, if I'll be free, I will also solve one example how to put this formula, and how to easily deal with this formula, and how to solve a particular problem for you. So I hope you find all this topic very interesting, and as you must go through all the points clearly, you must go through all the both the figures, and you must see how I try to solve it for you people, right? How I prepared all these things for you. So because I don't think so that, as I'm a professor in Dr. Mchem Institute of Chemistry, I have never seen any other teacher explaining in this way to any of the students. So this I would end up my lecture with this message, that I think others, my seniors, though there are only few seniors now left in my institute, so they can also follow, and they can also make you understand their views. They can also share on the YouTube, and that would be easier for you to catch, because when the video is there, when a video is available there, you can easily switch on, and you can see whatever you have missed in the class, or whatever you have missed face to face. So online has some benefits also, and if this thing is provided on YouTube, then it is easy to access, as YouTube is accessible to everybody nowadays. So I think I'm quite successful in this series of giving you different lectures on instrumentation. Now I will see if I find something more interesting related to XRD analysis. I will definitely share it with you. I will share the instrumentation methods, or I will try to find out whatever I think I would find easier to understand and easier for you to understand, because as a professor and as a PhD professor, I have operated all these instruments. I have an experience of operating XRD. I have an experience of operating thermogravimetric. I've done thermogravimetric analysis in detail, and I have also done the NMR, proton NMR. I have operated at Karachi HEJ University, and in olden times, it was in National Center of Excellence in University of Sindh, and Dr. Abdul Wahab Khanzada, late Dr. Abdul Wahab Khanzada, he was our teacher. He used to teach us, so I may pay some tribute to him also. He also explained few things about NMR, though he never shared his knowledge to any other students more. But I was, privileged. I had a privilege to share a few things from him, to get knowledge from him, and I would like to share my teacher, my supervisor, Dr. Muhammad Yar Howard's name. He's my mentor. Whatever I am today is just because of Allah Pak and because of Dr. Muhammad Yar Howard, who is a professor emeritus right now, mashallah, and he's a full-fledged working scientist at High Tech Institute of High Tech, so in the University of Sindh. And I would like to pay a lot of thanks and a lot of gratitude to my supervisor who has supervised me in my MPhils and in my PhDs also. So this lecture today is particularly for the PhD students who are doing XRD analysis, who are stuck up with XRD, who doesn't know what is Bragg's law, who does not know what is Bragg's equation. So this video would be helpful for all those. I hope I'm quite successful in explaining all these things to you. I will meet you again in my next video. Hope you will enjoy and you will learn something from this video. Thank you so much.